Okay, we posed the question. 1 kilogram of average earth stuff. And by that, I mean, put the earth in the blender. Don't really put the earth in the blender. You want to find a big enough one anyhow. But if you put the earth in the blender, blend everything together, all the compressed iron at the core and all the metals and all the silicon and all the other stuff, okay? Because earth is, biggest part of earth is iron, but it's sunk to the middle. Okay, there's still plenty of it on the surface. We're not going to run out of iron anytime soon. There's also silicon, okay? Whole lot of that. Good bit of aluminum, okay? It's hard to get out, but it's all over the place. Okay, well, anyhow, you got all that stuff. On the average, there's 20 moles of it, ballpark, between 20 and 30, okay? So I'm just saying 20, pick up a number. There's 6 times 10 to the 23rd atoms in every mole. And there's 6 times 10 to the 24th kilograms of mass in the earth. Okay, that's 3 things, right? So what are we going to do with those 3 things? Well, think about it for a minute. Tell me what we would do with them, whether you get the scientific notation or not. How would you set up the calculation? Okay. So what are we going to do? Well, these things in order. You got about 20 moles in a kilogram, right? And 6 times 10 to the 23rd atoms in a mole. Okay. So okay, 3 moles per kilogram, 6 times 10 to the 23rd atoms per mole. That gives you 6 times or 20 times 6 times 10 to the 23rd atoms per kilogram. Or 120 times 10 to the 23rd atoms per kilogram, right? By 20 by 6. And you still got 10 to the 23rd, but that's not scientific notation anymore. So you want to make that point. In scientific notation, you want this number to be between 1 and 10. Okay? So to do that, I say express 120 as 1.2 times 100. Fair enough? Okay, so that's 1.2 times 100 times 10 to the 23rd atom. And that's going to equal, so 100 is 10 to the second, right? And then you got times 10 to the 23rd. And that's atoms per kilogram. I'm writing that really sloppy. It's so small you can't even read it over there. But it's atoms per kilogram, so I'm going to keep that. To remind myself of what I'm calculating, right? So 10 to the second times 10 to the 23rd, usually 1.2 times 10 to the 25th. Atoms per kilogram, right? And if I write out the meaning of my calculation, He can serve as a guidepost to the way to actually do the calculation, okay, to actually get the right answer. Because I got the number of atoms per kilogram now, but I want the number of atoms in the earth, right? So can you take that quantity and write it out in a similar way, you know, how many atoms per whatever, or what, you know, what's the meaning of each calculation? And see what you get. Okay, you know, I should have it here so I can hold up for the camera. Okay, what we got here is 2 kilograms, which is about 4.4 pounds, about half a gallon of water, okay, of brass. If you blended the earth, the average density would be fairly close to what this is, okay? It's pretty dense, but you know, there's a lot of iron in the earth. And there are a lot of other heavy metals, but not nearly as much as there is iron. Now that's 2 kilograms. How many atoms would there be in 2 kilograms? Well, this is how many atoms per kilogram. That's how many atoms in 1 kilogram, right? So should be fairly obvious. We double this. Now, if we want the number of atoms in the earth, we would multiply the number of kilograms in the earth by the number of atoms in a kilogram. Okay. Well, that would be the 6 times 10 to the 24th kilograms, multiplied by 1.2 times 10 to the 25th. Atoms per kilogram. And that comes out 7.2. And I think I've heard that answer. Times 10 to the 49 atoms in the earth. Okay. 9, 8, 7, 6. I'm not sure what. Okay, 48, 24, and 25. No, 24 and 25, 49. So what's 24 and 25 is 49. Hang on a minute, let's discuss this. Okay. Well, that's the sun's ballpark 10 to the 30th kilograms. Okay. And there are about 100 billion stars in the galaxy, and the sun is pretty much an average star. Okay. Okay. Now, figure a trillion galaxies. Okay. Let's be careful. Let's call this the Milky Way galaxy. about average. This board's kind of rough. It's not, I'm not very long. I'm not being that careful about my writing either. Okay, so that's the universe. Okay. So how many atoms you got? I think you can work it out. Okay. So we have all this information. Well, first calculation you might do, we could multiply the mass of the sun by the number of stars in the Milky Way, because the sun is an average star, and that gives us total mass of the stars in the Milky Way, right? So one piece of insight is, and you don't have to start that way. You could start by multiplying the number of atoms in a kilogram by the number of kilograms in the sun, right? But we'll go with this. Okay, so how that works, okay? Number of kilograms in the sun times the number of stars in the galaxy. We could even say equals number of kilograms in an average star. The number of stars in the galaxy, right? And that would give us kilograms in the galaxy. Well, that's a useful thing. Now you might just stop and think, well, if you multiply then the number, if you assume the average density of the stars is not the same as the average density of the Earth, which isn't quite true. Yeah, mostly hydrogen in most stars, but you know, more solid core, very similar kind of to the structure of the Earth, except it's not solid. Well, anyhow, you get this, okay? So if we multiply that by the number of atoms in a kilogram, we're going to get the number of atoms in a galaxy, right? You know, some approximation thereof. Incidentally, we know how long it takes the Earth to go around the sun, and we know how far we are from the sun, so we figure out the mass of the sun. Okay, so we don't have to assume that it has the same density as the Earth, which is not quite true. Okay. Anyhow, there it is. Okay, so now what could we do with that? Well, one thing we could do is we can multiply that by the number of atoms in a kilogram, right? Let's just go on with the new information. Figure a trillion galaxies. Okay. So and what I just wrote there is what that's right. Number of galaxies times the mass of the average galaxy gives you what? Okay, got a quick answer and a good judge for mass of all the galaxies. Okay. Now I'm gonna. I'm gonna say it like this. Number of galaxies times the mass of the average galaxy, assuming the Milky Way is about average, okay? Would be about then number of galaxies times the mass of the Milky Way, which is the mass of all the galaxies. At least some approximation. It's not exactly equal because we don't really know how many galaxies there are. We've got a pretty good idea. Okay. Mass of all the galaxies, or the number of kilograms in all the galaxies. We'll remind ourselves that the mass is in kilograms. Now, why is that important? Well, we want to find the number of atoms, right? So we multiply that. Number of kilograms in all galaxies times the number of atoms in a kilogram. Number of atoms in all galaxies. Okay. That's how you want to reason it out. Before you write any number, you want to write something like that out. You want to write it out in words so you're sure that you have it right, so you're understanding it, because as soon as you write the numbers, you're a step away from understanding what the numbers are telling you. Figure out what the numbers are telling you, then put them together, right? So what we would get. We can do the number, that's easy. So there's 100, there's 100,000, there's 100 million, and there's 100 billion. Okay. I didn't write that out. Let's say 100 kilograms per star times 100 billion stars. And this is 10 to the what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I said 10 to the 10th a while ago. Yeah, 10 to the 9th is a billion. Thousands 10 to the 3rd, millions 10 to the 6th, billions 10 to the 9th, trillions 10 to the 12th. And after that, you can name them quadrillion, quintillion, sextillion, septillion, and nonillion, decillion, all that stuff, but just powers of 10, okay? Now you got 10 to the 41st kilograms, right? And then okay, well, trillion galaxies is 10 to the 12th. that gives you an estimate of 10 to the 53rd kilograms in the whole blame universe. Okay? Then you multiply that by your 6 times 10 to the 23rd. You get the number back. And the estimate, I think, comes out a little, I think it's a little higher than that, but it would be 10 to the 76. Okay? 6 times 10 to the 26, about 10 to the 70. 6 times 10 to the 76, which would be close to 10 to the 77. Okay? Now I haven't accounted for density and some of the stuff. So I'm not going through the physics of it, although it's actually fairly straightforward, but not something you want to deal with right now. Okay? I mean, yeah, the physics of stars gets really, really complicated. But the physics of orbits, mass of the sun, and get a more accurate estimate. Okay? And then you get the composition of the sun, which really has more moles per kilogram on the average than the Earth does. There's a lot of hydrogen and helium. Okay? Okay, well, we're still. Two things you need to know to get into the polynomials, okay? One is how you add them, like, okay, well, let's do this first. Let's say you got 2x squared plus 4x minus 7. That's a quadratic, it's a polynomial, right? Plus 5 times x squared minus 3x plus 9. Well, your distributive law says you multiply everything in here by 5, right? So this is pretty straightforward. You got 2x squared plus 4x minus 7 plus 5x squared minus 15x plus 45. We just multiplied all these by 5. Everybody okay with that? Thanks. And then you got 2x squared, 5x squared, plus 4x minus 15x minus 7 plus 45. How many x squares do you have? You got 7. How many x's do you have? Well, that's a minus 11. Negative 7, 45, 38. Okay? That makes sense? Now, the thing is, you got to know, and of course, Open Math will tell you this and reinforce it, is you can't add 5x squared to 4x. Okay? It doesn't work. If you'd like wanted to say that, well, I can prove it to you formally. I'm not going to take the time to do that. The rule is you just can't add unlike terms. And there's a good reason for that. It comes back to the distributive law. I'll tell you about that a little more next time. But right now, you can add x squared to x squared. You can add x's to x's, but you can't add x squared to x's. You can't add different powers. Okay? When we get a little further into fact, I'll tell you a little bit more about it. That's a rule. Okay, now the thing that was mentioned is this, okay? This means this plus a -1 times all that. Negative in front here means you add a -1 times that thing, okay? And that's 3x squared plus 2x minus 5 plus what? -1 times x squared plus -1 times 6x plus -1 times -9. Okay? So that's a distributive law. You're multiplying everything by the -1, just like you multiplied everything by the 5 up here. And that equals 3x squared plus 2x minus 5 minus 1 times x squared is a minus x squared, so plus or minus x squared would just be minus x squared. And this is going to give you minus 6x. This is going to give you plus 9. Now, what happened is the same thing that would happen if you just understood that this is the case, and just go through and change all these signs. Because you change the sign of x squared, you get negative x squared. Change the sign of 6x, you get negative x. Change the sign of negative 9, you get plus 9. Okay? Make sense? Definitely. So I'm not sure if we're going to explain it that way in open math, but since the question came up, that's why you change all the signs. Of course, if I multiply by negative 5, then I get negative 5x squared and plus 15x and minus 45 and all that stuff. Okay. Now, what's 2x plus 3 times 5x minus 4? Well, the distributive law tells you two ways we could write this. I'm going to write it this way: 2x plus 3 times 5x minus 2x plus 3 times 4. Because if I multiply a number by 5x minus 4, I'm multiplying that number by 5x, then I'm multiplying it by negative 4, right? So the number I'm using is 2x plus 3, which isn't just a number, it's a symbolic thing, but it still stands for numbers. Okay? So it's 2x plus 3 times 5x, and then you got the minus sign there, so it's 2x plus 3 times negative 4, or minus 2x plus 3 times 4. Okay? Now that in turn equals 2x times 5x plus 3 times 5x, just to get started. 2x plus 3 multiplied by a number is 2x multiplied by that number plus 3 multiplied by that number. And then you're going to have minus the quantity 2x times 4 plus 3 times 4. Again, 2x plus 3 times 4 is 2x times 4 plus 3 times 4. Okay? Got a question? Okay, we do this. It gives us 10 x times x is x squared. 2 times 5x is 15x. And then we do what's inside the parentheses first, which gives us 2x times 4 is 8x. And 3 times 4 is 12. And then we're going to get a minus 8x and a minus 12 when we distribute negative 1. And that finally gives us 10x squared plus 7x minus 12. Now, what has effectively happened here, and I don't really like to see it, but I did it. So, what you got. And what ended up is if I just multiplied everything by everything. Everything in here by everything over here. So multiply this by this, and this by this, and this by this, and this by this. Okay? So go to it. That should give you some kind of a start. So I'm gonna go ahead and make that assignment. We'll see how you do on it, okay?